afternoon. On behalf of the Director of the Austrian Center for Digital Humanities, Alexandra Lenz, it is my pleasure to welcome you to another edition of the ACDH Lectures at the Austrian Academy of Sciences. In this lecture series, the ACDH invites well-known experts in the field of digital methods to share their knowledge and provide insights into their work. Our today's guest is Roland Fleischhacker. He has been working in the IT industry for over 35 years now, and he's the co-founder and CEO of deepsearch, a software company based in Vienna specializing in neuro-symbolic artificial intelligence. His current work focuses on areas such as natural language understanding, business processes, process automation, and artificial neural networks. In addition, he teaches at the University for Continuing Education in Krems within the Generative AI Certificate Program. The title of his lecture today is Beyond Correlation, Causal AI Decisions Based on World Models. And while our current AI debate is largely dominated by generative models based on the statistical recognition of patterns, Roland Fleischhacker will introduce a different perspective. His approach focuses on a new technology that uses an explicit world model to recognize conceptual causalities rather than merely correlations. With this approach, AI decisions can become more transparent, traceable, and reliable, which is also an essential prerequisite for the meaningful integration of AI into research processes. We are therefore very pleased that Roland Fleischhacker accepted our invitation to give this ACDH lecture today. And we are looking forward to your talk. The floor is yours.
Yeah, thank you very much for this nice introduction. I think there's everything said which has to be said. Thank you. It's really a pleasure and an honor for me to be here in these holy halls of science. I wanted to start with a note that I am not a scientist, I'm not a researcher, I'm a simple engineer, and an entrepreneur. So I ask for your understanding that probably the level of what you're used in lectures like that from the academic standards, I won't reach it, but nevertheless, I hope that my lecture will be inspiring for the one or the other. The technology I will present today, in a few minutes, is topic agnostic by definition. It's about, you heard already, natural language understanding, which means everything and nothing. Yeah? What is natural language understanding? And so what I will do before I go into technical details, I want to give you a little bit context where we use this technology. And as I mentioned, you can use it for a lot of different use cases, but we optimized it for certain use cases where we are busy, where we make our money. Before I go into details, I would like to give you a short introduction to our company, deepsearch. We are there, I think 300 meters from here, Fleischmarkt. So it was a very short way to come here. We founded the company in 2010, so 15 years ago, 16 years ago nearly, with one goal: to teach machines to understand colloquial language and to use these information to be able to process it. So to reach a gap between unstructured language, to structured processes. That's our goal. The first 7 years we spent with research and development. So at that time, maybe I was a scientist. We received very little support from the public side, from public grants, because the juries judged that the idea we had was too utopical. So we didn't get any money, but nevertheless, we managed to build this system and to improve it. And so I said already, you know, understanding causal language means everything and nothing. Yeah? And that's not a good starting point if you want to go to make business. So we said we have to focus and to sharpen our profile. And we said, okay, where can we use this technology to understand? We said customer care. So we decided to build a system which supports companies with a lot of customer service contacts to support them. I will show you in a few minutes what kind of use cases we support. And there, even more focus on companies with a huge volume of customer contacts. And then again, more focus on regulated industries. And remember, that's already a hint for what I will tell you in a few minutes. Why regulated industries? Because they have very strict rules for auditing rules. So they have to document, to monitor the processes. They must be able to explain all their decisions. Remember that. I will come back on that a little bit later. So typical use cases you can see here. It starts from simple routing emails, calls. We also provide voice bots, chat bots, but not the ones you know already, which doesn't work well. We are the others. Because our chatbots are also able to solve even complex questions, yeah? to open a dialogue with a customer. Because, you know, especially in customer service, it hardly happens that a customer knows exactly what he wants when he phones or when he writes to the customer service department. Quite often because the person is not able, you know, they are not specialists for, I don't know, some technical issues or so. They're just describing symptoms, yeah? Or sometimes maybe they are ashamed to say exactly what they want. Yeah? So because, you know, they can't pay the bill, and then they are talking about the high inflation rate and that their children are studying somewhere abroad, takes a lot of money. Actually, he wants to say, I can't pay the bill this month. And so what I wanted to say is sometimes you have to guide these persons to identify what they really want. Yeah. And then what you see here in the middle is what we call agent augmentation. This is, you have to imagine you have a call center and a person calls and talks to a person in the call center. We call that call center agents. And so a human talks to a human. And our AI sits in between and listens to this conversation and interprets it in real time and provides the call center agent with questions he or she should ask, with information, at the end, hopefully with solutions. So, because you know, you have two kind of company types. One, they say we want to save as many costs, so the more automation the better. And we have other companies, they say our clients don't talk to machines. They are allowed to talk to to people. We support both, actually. When we design our customer solutions, we use a wide range of AI technologies, from simple neural networks to complex large language models. And what you see here is a rough diagram. So you have the client, you have several communication channels like telephone and email and post letter and so on. Then we have a communication layer which is only responsible to receive the messages and to send the messages. And then the very important one is the decision layer, which takes the messages, tries what is the topic, what is the message about, and then it triggers a certain process or answer in the execution layer. In this talk, I will only focus on this decision layer and not on other technology, because, for instance, when you at an insurance, someone sends a picture from a car accident, and our system, as I will show you afterwards, is not able to interpret pictures. We are really focusing on text, but we use large language models to say, please describe the picture, try to identify which type of cars, what are the numbers and so on, and we get this text from the photo interpretation, and that our system again analyzes it, extracts relevant information, and tries to find out which business process do I have to start. We are living in a quite paradoxical age. On the one hand, we see a quantum leap in text generation, natural language processing by large language models. And on the other side, we know that these are just enormous statistical machines. What do? They learned the internet or read all the internet, and what they do is they calculate the next token from a given set of token. And to be honest, I'm always again surprised how well it works, though it's just a statistical method. But I don't know exactly who was a lady who invented the name of the stochastic parrot, which to my mind describes the machine at a terrific level. But actually it's a problem, if we are just predicting the next token, so there is, to my mind, there is not really intelligent. This is a statistical machine. And especially in important decisions, I think it's better to have a logical reasoning than a good guess. And that's what I would like to introduce now, deepassist, which from our perspective is a leap from statistical correlation to causal reasoning. And that's what I wanted to show you. Let me begin with a table where I show you some main differences between generative AI and neurosymbolic AI. The first one is the basic unit we are processing, a token in a generative AI, and These tokens have an average size from 3 to 7 characters. The latest system tend to use whole words as token, whereas we are not talking about words or fraction of words, but our tokenizer identifies concepts. So this is a very important difference, and the concept also can have more than one word. Yeah, think about code of contact or the plat du jour in French. So we have in German we tend to use compositors. So we add noun after noun. In other languages we quite often use more words to express a concept. And if you have identified the concept and you have identified another concept, the big advantage is that you know what you are talking about, and you know that the combination of certain concepts makes sense or don't make sense. And I think this is the main difference, that a neurosymbolic AI has the ability to know what it's talking about or what is reading. The abstraction layer or abstraction method with generative AI is a vector space, which is fundamental, a brilliant idea, because what does it mean? You transform text to vectors and suddenly you have all the methods mathematics can offer you. Yeah? And we know, especially in this auditorium, what that means to use mathematical methods. But it comes at a high price, because the vectors you have to use here have dimensions more than 1,000. So it's really impossible for a human to understand these vectors. With our technology, we use what we call semantic space. Let me explain what we mean with that. I want to give you an example. If you have a fact what you want to express, then for us, semantic space means all sentences you can form to express this fact. So, and if you have a sentence which expresses exactly that what it should represent, it's at the very center of the semantic space. If it's a rather vague expression, then it's rather at the edge. So if I want to express, for instance, that I'm sitting in my car and driving to Salzburg, and I say, I'm sitting in my BMW on the A1 and drive to Salzburg, this sentence is exactly in the center of this semantic space. If I say, I'm heading towards the birthplace of Mozart with 130 kilometers per hour, it says nearly exactly the same, but it's rather on the edge. Yeah? So the more, maybe you know, in the past there was a show in the US, now I forget the name. Yeah, which actually worked with that. I can't remember the name now anymore. So, oh, sorry, this is not what I wanted. The next difference is that the training data, today's artificial intelligence systems need data. The fuel of artificial intelligence today, who knows what will be in 50 years, I don't know, but today is data. And generative AI has a simple method. They read the internet. Yeah? So they have a lot of text. This has advantages because it's a lot of text. It has a lot of disadvantages because it's also a lot of rubbish what it reads. Yeah? And you need a special method called reinforcement learning to keep all that rubbish under the carpet. But that's another topic. We have another approach. We have a world model which has advantages and disadvantages. The advantage is that it's a condensed, structured database of knowledge. And you don't, every time you rebuild the model to identify and to rebuild all your rules, what you need, and all the things you want to identify, because you have it condensed in a knowledge graph. We'll go in detail a little bit later what this is from the technical point of view. Then we have the decision mechanisms. In GenAI, these are weighted parameters, yeah, depending on the model. They started some years ago with some millions. Now we are reaching, so GPT 5.2 is said to have 100 trillion weight tokens, so quite a lot. We don't use neural networks, no weighted parameters, but we use rules. We are a deterministic system. That's probably the biggest difference between the two systems. But one question I will answer a little bit later. Everyone should ask, 60 trillion rules, how can you manage that? It's impossible. And I will show you how we do. What's quite interesting is if we look at the 100 trillion weighted parameters and we look at the 60 trillion rules, we have quite the same dimension. And what I don't know, is that a coincidence, or is there some deeper, I don't know, understanding or reason behind it? I don't know. So what I said already is we do reasoning on a causal basis, not on correlations. This has as a consequence, we are a glass box. And you remember when I said we are focusing on regulated industries because they have strict audit rules. With our technology, the auditor can read why the AI took a certain decision and not another one. Also sometimes why it took the wrong decision. Especially in debugging systems, it's very important to know why it was the wrong decision. And then there are also some, let's say, not so much technical, but rather ecological differences. Our technology is fine with CPUs, whereas generative AI needs huge farms of GPUs. And the second last line, this is not a typo. Yeah? If you create a new model like GPT-2, there are estimations, they don't publish it, but there are estimations that they produce about 50,000 tons of CO2. If you generate a model with deepassist, we generate 100 gram CO2. But we also must admit that generative AI has much more possibilities than this. And this is probably what I will be, so one of my conclusions, that there is not one technology, there are dozens, and the art of AI design is to use the right technology for the right purpose, for the right problem. And today, to my mind, it seems a little bit that these AI technology discussions get an ideological touch. You know, if you don't use generative AI, then you are someone from yesterday. Yeah? And this is not even AI. Yeah? But I think that what we will see that afterwards, composite AI, this is the real engineering art to find a balance between what do I need and what do I have to invest in it. Yeah? And what I can say is that in a certain topic, we will see that in our technology, neurosymbolic is at least as capable or good than generating when understanding text. What we can't do is interpret pictures or generate poems in the style of Shakespeare. That we can't do. That year you have to use generative AI. So, we saw a little bit the differences, and I want to go now into detail, starting with the world model. I mentioned the world model already several times, and I want to explain this to you. The world model is one of the core elements of deepassist, and from the technical point of view, it's quite simple. It's an RDF format. It's a triple store. Anyone who has worked with ontologies knows that ontologies are really a great tool to work with, but they can quickly turn into a nightmare in terms of maintenance, updates. So in a very early phase of our design process, we decided that we have to keep this knowledge graph as simple as possible. Otherwise, we will ruin ourselves by maintaining this knowledge graph. And at the very end, we have 6 relation types. So maybe for the ones who didn't work so much with ontologies or knowledge graphs, a knowledge graph consists of nodes, yeah, and they are connected by relationships. At the very end, it symbolizes or it implements a basic feature of all languages of the world, which what they have in common is that they use this this combination of subject, predicate, and object to transport messages. And you can read these things. You can say, so what we have here is a car, you're here in the middle, you have a car, and you can say a car is called a car, or a car is called a heap. So you can read these constellations. And our world model, yeah, is technical, such a knowledge graph, depends on the industries between 200,000, 400,000 nodes and several millions of relations between them. And this world model has virtually 3 layers. The first layer, and by far the biggest, covering about 95% of all nodes, is that what we call common sense. Then we have a layer we call domain-specific layer or industry level. You know, every industry has its own vocabulary, its own concepts, and they are in this middle layer. And then we have a very small individual layer for the customer, product names and things like that. If I say common sense, that's a little bit. I have to relativate that, because I guess in this room here we have probably, and this is really high, active vocabulary for about 15 to 20,000 words. I didn't count it, but as far as I know what I read, well-known boulevard press or boulevard media, they have about 600 to 800 concepts when they write their articles. Yeah. We have about nearly 200,000, and we call it common sense. So you can imagine this is more than common sense. Yeah. I want to answer a question I get often asked is, how did you build that? And I want to ask that, or to answer that in advance. It was blood, sweat, and tears. You know, we sometimes are open source, some content we bought, and a lot of content we extracted from documents from our customers. And it's also important to say this is a process, you know. Now it's relatively stable, yeah? Especially the common sense layer, because language is not that dynamic. Yeah? Where we see changes are in the domain-specific layers. If we have new industries, if we open up new industries, we have to add this layer for the specific domain. But all in all, we have a very stable basis. What we do is for every industry we have an own world model. Maybe I also would like to give a short explanation. What are the relations we use, these 6 relations? And it's also quite important, in the last 10 years, we cancelled one relation because we found out that it's rather disturbing than helping, and one we added. Yeah? And the relation types will be very familiar for those of you who are dealing with language, is synonyms, hyperonyms, holonyms, or meronyms. And the 6th one is instance of. But this has not so much from the, or let's say it has more resource or optimization feature. Can give you an example why. We invented this new relationship, is instance of, at a project at the Deutsche Bahn. And you know, you have the concept railway station. And then you have, Deutsche Bahn has about 16 or 18,000 railway stations all over Germany. And so in the past, all these railway stations, yeah, like München Hauptbahnhof, but most of them say, or write München HBF, and some say Hauptbahnhof München. So you have also different spelling for this concept of a certain railway station. We had to add all these as hyperonyms to the knowledge graph, which meant that in situations where we're just happy to say they are talking about a railway station, we had to carry all the railway stations all over Germany. And now imagine that with the concept of mountain, yeah? And you import all the mountains of geonames. So this leads to huge, or the language models are always huge, but even to huger language models, though you don't need it. And huge language models, what does it mean? Long processing time, so it doesn't run 2 hours, but 20 hours. Yeah? It doesn't respond in 50 milliseconds, but in 150 milliseconds. So we decided to create this instance just to get more performance. That's the only reason. So far from the world model. Before I go into detail about how we use this world model, I want to explain a little bit about correlation versus causality, even though I don't need to explain the difference in this auditorium, but I know that maybe some other listeners are not so familiar with that. So that's why I want to explain it just in a short example. If you have a hot summer day, then ice cream sales increase, but also the amount of sunburns is increasing. So a correlation-based AI may say don't eat so much ice cream so that you don't get a sunburn. And you can think that further. Say, if rising ice cream sales lead to an increasing consumption of sugar, and the increasing number of sunburns leads to increasing number of skin cancer. So the correlation could say, AI could say, don't eat so much sugar, otherwise you get skin cancer. And all these things, of course, totally nonsense. And that's the pitfall of correlations. And that's the difference between correlation-based systems and that what we do, causal AI. So we don't ask what is the next best word following sunburn, but we navigate through the knowledge graph and get the information, what is a sunburn? Yeah? Why does it come from? Yeah? What does it lead to? Yeah? So we gather in a basket all these information, the surrounding context, and it's not just the word sunburn, it's the concept sunburn and all the knowledge around it. So this was a short sidestep to correlation and causality, and now I would like to explain actually how the system works. You know, the goal is a language model covering all the semantic spaces we need. That's where we're heading to. And where do we start? We start with a world model, having basic understanding of the world. And I want to emphasize again, when we talk basic understanding of the world, that means basic understanding of the world in that ecosystem we are. So we don't have like, I don't know, physical or chemical truth in it, because we don't need it. Yeah? And well, this world model is exactly that, what I just explained. And now I want to introduce probably the most important step in solving this problem. When you remember, I said we had 60 trillion rules. Yeah? How can you manage that? And what we did is we invented a programming language. We call it deep semantic markup language, which describes semantic spaces. Here you have one statement of this language. And what did you see? You have group is an operator, and it's an operator on 2 pointers, 2 concepts in the knowledge graph. In this case, lose something and found item, or you also could say lose something and lost object, means that you want to build the semantic space that someone says, I lost something, but not the patient's, something physically, the key, the iPhone, the purse. And with only this single short statement, you can create this semantic space. And then you can add more such statements. And if you calculated how many rules this statement in a normal knowledge world graph generates, it's more than 6 billion. It sounds quite simple to say I lost something, but there are so many different possibilities to say it that and there are especially so many things you can lose, yeah? Because this system also reacts if the Pope says I lost my mitra, yeah? Because the system knows what the mitra is. And it also knows what the Pope is, of course, yeah? But there are so many possibilities, and that's why we reach these enormous number of rules, because even the single statements generate already a lot of rules, but it's quite simple, you know. So you don't need a PhD in computer science to program this language. A lot of our customers, the people of the department, of the customer service department, retrain or train the system themselves, because they just have to know what they want, and to cover it in this syntax is very simple. And to make it a little bit easier, or even easier, what you can do is you can collect some certain statements to what we call a semantic building block. And you even can add a kind of or parameters, because you can say, I lost something, but most of the time you add not only what you lost, but where. Yeah? So the location. So you say, I lost it in the office, I lost it in the train, I lost it in the taxi. But the basic semantic space stays the same. So you can build, or we build, a building block which covers the semantic space, and as parameter you can give the location where this person says. And when you say, I've lost something, and you give as parameter railway station, then the knowledge graph knows that the railway station consists of a hall, it has toilets, it has a waiting room. So you also don't have to care about what rooms are in there, because the knowledge graph knows it. And we have about, I don't know exactly, I have to ask my colleagues, but probably nearly 6, 7, 8,000 of these pre-configured building blocks. And you can see it as a kind of Lego blocks, where the children play with. So you don't have to care what's in that building block. You just use it, and you can trust that it will work. And if you add several of these building blocks to that, what we call topic of interest, that's actually what we know, what we have to identify for a customer. Also, these topic of interests quite often represent a certain business process. Yeah? So that if someone says something, we identify the process and we can start it. And all these topic of interests, some of our clients have several dozens or only 10, others have thousands of them. And then we have a process, a model generator, and it's actually a kind of compiler which compiles all these statements to a language model, and then you can use it. And yeah, so if we look at the architecture now from, let's say, a 10,000 feet perspective, then it looks like that. What we see in almost all other AI systems, we have training data, we have a machine learning algorithm, and we have a neural network, which is a kind of black box. And then you send in real-world data and get a result. That's what we call learning by observation or by perception. We added this with another kind of learning by instruction. By using the knowledge graph and using the semantic building blocks and the semantic markup language, we have, let's say, an editable part of it. And I always say it's not so different from how we people learn. We learn a lot by observation, yeah? But we all have to go to school for several years so that we don't have to learn everything by trying out. So we get it condensed knowledge, and that's actually quite a similar approach. Yeah. And after generating the model, we have this causal language model, and we feed this with real-world data, and not just get results, but we get explainable results. And what I will do now is I want to show you, or to give you the possibility to watch the AI thinking. I brought an example from The world model you see here is from a client, is Vienna Wohnen. Maybe not all of you know that about 1/3 of the population of Vienna lives in apartments owned by the city of Vienna. That's why probably one reason why the rents are, compared to other cities in Europe, quite reasonable. And they have a call center, very big call center, 724, where all these around 600,000 people who live there can call there day and night, 365 days per year. And this is really, they have a huge collection of topics because people call there, you can't imagine. It's more, sometimes more like a psychological helpline than a customer care hotline. For this example, I used this world model, and what you will see is you have this white input box, and there will be input of a short sentence. It will be in German, not in English, but I hope most of you also understand German. And then you have the grid here. And the grid represents about 1,200 business processes, which at least one should be started after the call center agent has identified what this caller really wants. And I will show you that. It will run in super slow motion because the process actually just takes 50 milliseconds. And I doubt that you can read so fast, so I play it in slow motion. And don't look at the white input box, rather look at the grid. What you see there are the hypotheses, you know? That's like the system works. It interprets the concepts, it identifies the concepts, it tries to figure out relation between the concepts, and it builds up hypotheses. And every rectangle will represent a hypothesis, and it has a name. Yeah? And the bigger the rectangle and the darker, the higher the probability score is. So the bigger, the better. And you will see that they will change because this text starts and we interpret it one letter after the other. So not at the very end or one word after the other, but letter for letter. And I will explain afterwards, what did the AI think about? Why did it come to these sometimes very strange ideas? And it's funny. So that's the end. So we know that the television receiver doesn't work. And I would like to first explain this sentence for, you know, this sentence, während ich Kommissar Rex verfolgte, by the way, Kommissar has a typo, wurde plötzlich der Schirm finster is a quite tricky sentence in German, because it has a lot of ambiguities. And that's one of the main problems in natural language understanding, especially if you have short texts. If someone is talking about A4, is it talking about chess or talking about the car or taking the paper size or the highway? Yeah? So you always need context to identify that. And maybe you realized that at the not at the very beginning, but at the beginning there was translated information or complaints regarding film or photo shooting. Ja? So Beschwerde über Foto- und Filmaufnahmen. You know, Wiener Wohnen has about nearly 2,000, I think 2,000 or 1,800 buildings, and they make a lot of films there, yeah? Like Kommissar Rex and Kaisermühlenblues and just name it. And you know, sometimes, well, always, then there is a lack of parking space, so people are complaining because it's all closed. Or if they have shooting during the night, people complain because it's loud and it's so light. So there is a certain process at Wiener Wohnen how to handle that when people call that they can't sleep because of photo shooting. And why did the system had the association? Because it knows that Kommissar Rex is a famous Austrian TV series. This is the only hint. That's why it disappeared quite quickly again. So it was the only word which really made sense for this, or the only concept which made sense for this hypothesis. Then we had, we had a hypothesis, Beschwerde über Mieter wegen Bedrohung und Belästigung, so complaint against the tenant for threats or harassment. Is also again Kommissar Rex, which is responsible for that. Because Kommissar Rex is not only a TV series, it's a dog, it's a German Shepherd, so could be rather dangerous dog. Yeah? It's not a small one. And there is the word verfolgen. Yeah, verfolgen has a lot of meanings in German. For instance, to track someone or to stalk someone, but also to watch. And if someone stalks you with a German Shepherd, maybe you get afraid. In this is the others, it's watching the dog, yeah? But not watching the dog, but watching the series. And that's why there was, for a short moment, the AI had the idea that maybe is a complaint about another tenant. Then you have also the word Schirm. If you remember at the very end, the Schirm wurde finster. Schirm has also a lot of different meanings in German. Yeah? So it's an umbrella, it's a sunshade, it's a shade, it's a shield. You know, have this iron dome is also a kind of Schirm, and you have the yeah, I think umbrella I mentioned already. So and of course screen, yeah, the most important one in this case, and. What the system did, it says, okay, what we see is that I am watching a TV series crime series, and the TV set breaks down. That's actually the interpretation of that the internal interpretation for the AI to find out what it's about. And the difficult is to find out all the different real concepts that are behind. So, before I'm coming to an end, nearly a pinpoint, I want to answer a question I often get. And why is deepassist better than Claude or ChatGPT or something else? And I always say, we are not better, we are different. In some use cases, are not even solvable with deepassist. But in other use cases, we provide at least equivalent results, but with a fraction of the costs. That as an add-on, including auditable decision processes, and that's today more important maybe that you imagine this question about European digital sovereignty is, of course, especially in this case, a very helpful aspect, because especially the companies we work in, the financial services, also in the utility, they get slowly enforced or to use mainly European systems, so to get independent from US hyperscalers. What I also see is during last, I think, 2-3 months, there were several foundations of new startups. The research chef from Meta, Jan Lecan, just founded in Paris a new startup founded by, I think, 1 million euros. The actually inventor of GPT from OpenAI opened a new startup, and also one of the co-founders of DeepMind founded a new startup. And what they all have in common, all three, is that they design software with world models, because they realized in their former companies that they're reaching a glass ceiling they can't break through. And now they try it with language models. Totally different technical approaches, but from the principle, it's about world models. And if you see here, this is the hype cycle from Gartner. Gartner is the most famous IT research company in the world, and they always make for certain technologies these hype cycles. Probably you know it. And it's quite interesting if you see, so on the rising part, you have neurosymbolic AI, world models, and causal AI. So I feel here very comfortable with our solution. The only thing is that they say this will be in 2 to 10 years, yeah? But we are ahead of our time. So it was probably a good luck and a good inspiration when we started 2000 or 2010, and I think 2013 we realized that we need something like a world model. So finally, I think the future will show us a lot of different technologies, AI technologies, and I think that most of them, all of them, have their value in certain situations. And the only thing I'm really sure about is that it remains exciting. Thank you very much.